So I'm very excited to introduce Ardjen Pengel, who I think has recently joined the University of Cambridge as a postdoc, and will be talking to us about output analysis for MCMC. So please.
Thank you, Sam, and thank you for having me and organizing this lovely conference. So today I'll telling you a little bit about Gaussian approximation and output analysis in the high-dimensional setting. And this work is joint work with Jun Yang, who is in the third row in the audience. He's at the University of Copenhagen, and Jojo, who is at the University of Toronto. Okay, so a quick outline of the talk. I'll first briefly explain the setting and the motivation, then I'll introduce the Gaussian approximation results, and then I will give the applications of these theoretical results in uncertainty quantification and output analysis for MCMC. So as we already know, our goal is often to simulate from some target distribution pi, and quite often we are interested in estimating expectations with respect to this distribution, which I will also denote by pi of f. And I will consider f that goes from Rn to Rd. It might be the case that you might be interested in less components or more components than the state space has. And yes, the main idea is, in general, we construct a Markov process, which it's such that its long-run behavior is described by pi. And we will consider the high-dimensional setting, where both the dimension of the state space and the amount of components we are interested in can be large. Okay, then we construct this Markov process such that it converges to the stationary distribution. So as time tends to infinity, the probability of your process being in a certain region of the state space will correspond with the amount of mass the target distribution gives to that part of the state space. And also, in order to estimate our expectations of interest by the ergodic law of large numbers, we can use the time average. This is, of course, all known. However, we have to keep in mind that MCMC is approximate inference. We cannot sample exactly from the target distribution, otherwise we would just do that. But only as t tends to infinity is our sampler giving us the equilibrium distribution. So that's why we have to carefully analyze the algorithms we have, and some are more appropriate for certain targets than others. So the following two practical questions are at the heart of every application in MCMC. So firstly, we need to decide when it is reasonable to assume that our sampling algorithm is indeed exploring the state space according to the stationary distribution. And the second question, even if we were to start in stationarity, how long do we let our sampler run? When is it enough? And a third question, how does the answer of these questions depend on the dimension of the problem? So of course the solutions are, to the first question is we just look at quantitative bounds to stationarity, we look at the mixing time, we determine a burn-in. In high-dimensional settings you often have you need some type of a warm start, a good initialization, and then you say, okay, after this time it's reasonable to assume that we are sufficiently close to the stationary distribution. For the second question, how long should we run our sampling algorithms? Then we will have to look at, okay, we are, for example, interested in pi of f, or posterior mean. When are we certain enough of this quantity we want to estimate? And this is often done with the termination criteria. So when I say uncertainty quantification, we have to look at the central limit theorem. It's already known that for a sufficiently high degree of polynomial ergodicity and a little bit more than a second moment, you have that the central limit theorem holds. Quite often in the, in order to estimate this asymptotic variance, in order to implement termination rules, in order to study them, you will also need this functional central limit theorem, which holds under the same conditions. So what this basically tells you, we look at the partial sum process of our empirical average, and the entire trajectory tends to a rescaled Brownian motion trajectory. So the entire trajectory of the estimation process of our time average is in some sense converges to a Gaussian trajectory. And of course, the asymptotic variance is a bit more complicated because we have all of these autocorrelation terms, because in general our chain, of course, will have dependence. Okay, so if we have the central limit theorem, we all know that we can construct a confidence ellipsoid for our parameter of interest, which is in this case just pi f. And yeah, we just make a confidence ellipsoid, and Q alpha can be a chi-squared or a Hotelling quantile. And the termination rule, which was at first theoretically studied by Peter Glynn in quite some time ago, but this was the first one that rigorously analyzed this termination rule. The termination rule is defined as follows. So when our confidence ellipsoid is sufficiently small, so when its volume scaled to the dimension is sufficiently small, then we can terminate our simulation. Because the intuition is, okay, we don't have to sample any further. If we are happy with some precision epsilon, then we can stop simulating. And of course, and there have been many other rules after this, you can let the epsilon depend on the norm of whatever you're interested in, so it is indeed a relative error is allowed. Okay, and in Peter Glynn's paper, it's shown that in order to analyze these termination criteria, you not only need a functional central limit theorem, but you also need its refinements. And the same holds in order to analyze estimators of the asymptotic variance. And why is that the question? You can think about it like this. We are actually following a confidence ellipsoid over the trajectory. So not only is this, you want the central limit theorem at the endpoint, but you want the CLT to hold over the entire simulation trajectory, and ideally it's a refinement. So what do I mean by the refinement of that functional central limit theorem? Is what we call a weak Gaussian approximation, which I will just abbreviate with GA. So on some probability space, we can reconstruct the process and the Brownian motion such that we can describe the magnitude of their difference. So how you can roughly read this is if you divide both sides by square root of 2, you approximately get the convergence rate in the functional central limit theorem. Perhaps I should have given the reference there. It's a little bit slower, but for this talk it doesn't matter. So this psi t will be something that goes to infinity, but at a slower rate than square root of t, otherwise the bound is useless, of course. And you can always see it as, okay, the partial sums tend to rescaled Brownian trajectories according to a rate that's roughly psi t divided by square root of t. Okay, the current best Gaussian approximation rate for multivariate MCMC samplers now is t to the power 1/4, and existing Gaussian approximation rates are not dimension dependent. So what we want to do in order for the widely used output.
When you say that, so that's the psi t is t to the
Yes, yeah, that's a psi t. So that gives a convergence rate of the FCLT of roughly 1 divided by t to the power 1/4. Okay, and so in order to have results regarding the analysis of variance estimators and termination criteria to carry over in high-dimensional settings, we need to obtain dimension-dependent Gaussian approximation rates. So yeah, indeed, how does this convergence rate depend on the dimension of the state space and of the amount of features we are interested in? So we'll spend a little bit time on some technical conditions. We consider a modified drift and minorization framework. So the M-step minorization condition basically gives a lower bound for the M-step transition kernel, and its interpretation is as follows. It tells you how fast the process forgets it's how fast the dependence decays in some sense, because every time the process is in this small set C, you have some probability alpha of drawing according to this small measure nu, which means that after M step, you will be independent of that step. This holds true for every high-order recurrent process, and quite often for many MCMC algorithms, you can even show that a one-step minorization condition holds. Okay, and the second set of moment conditions, this is very standard to consider in this Gaussian approximation setting, we often consider, okay, we have p moments where p is strictly greater than 2, and because we're in a high-dimensional setting, we assume that we have a uniform p moment over all the coordinates. That's A1, and in A2 we'll just assume that the moment generating function exists for all the components. Now we can state our first main result. So I will assume that X satisfies a stable geometric drift condition. I will tell a bit more after that. But basically the idea is that this small set C, the chain fidgeted sufficiently often and you have some geometric drift towards that. And now I'm assuming a one-step minorization. In this case,
you assume that there's a very small set in your enormous sample space, then you see it often.
yes, yeah, and the process drifts quite often to that, something like the bulk of the mass, you can imagine. Yeah.
And C is small.
Ideally, yes.
You live in a different world than I do.
So theoretical definition of a small set is very.
Yeah, but for every this exists for every Harris recurrent process. This can be done, and we don't need to know the set. It's just that it theoretically exists. We don't need to know it. It just needs to exist. We will not use this set, and you will not, when you're having your sampling process, you don't need to know when you're in this set. It just need to theoretically exist. And it holds for indeed every positive Harris recurrence process admits this minorization condition, so such a small set condition holds for the M-step skeleton chain. Okay, what do we have then? In the case of geometric drift and one-step minorization, we have the following dimension-dependent Gaussian approximation result. The first thing we see, we get the t to the power 1 divided by p, which is actually up to a log factor the optimal rate you can get for independent random factors. And our dimension dependence is linear in the dimension of the amount of components you're interested in, and it depends on the dimension of the state space through the drift and minorization conditions. So how you can look at this, if you divide everything by square root of t, you would get the central limit theorem. So if you were just considering, okay, how is my dimension of the Markov process allowed to grow such as the CLT holds, then it should grow at rates smaller than square root of t.
What is n?
N is the dimension of the state space. So F goes from Rn to Rd, and N is the dimension of the state space, and D is the dimension of the amount of things you're interested in. So N can be equal to D. D can be equal to N. Okay, what we did next, we also considered the same result under a polynomial drift condition, and then we obtained the following rate. So this approximation rate is strictly slower. So what you see is that the P0, Q, is actually the rate of polynomial ergodicity. So the rate is a mixture of the amount of moments and the rate of polynomial ergodicity. So if I assume that the polynomial drift is strong enough, so almost exponential, then I recover the P of the exponential drift case. Whereas if I assume that every component satisfies a moment generating function, then the approximation rate is solely determined by the speed of ergodicity Q. And in the case in between, we obtain some mixture of P and Q. And in this case, we also have, that's for large P and large Q, we have that the dimension can grow at most must grow slower than square root of t. Now we consider the more general case where the process only satisfies an m-step minorization condition, and of course we also have this result for exponential drift, but I will only give it for polynomial drift. Then we get the same dimension dependence, but we get a slightly slower approximation rate in the weak Gaussian approximation. So now for large P and Q, the dimension would only be allowed to grow as the 1/4 power of t. Okay, now some conclusions of these results. So one thing that we do require here, like differences between the between the multidimensional setting, is that our family of drift functions should remain stable as the dimension of the state space grows, which in the exponential drift case is just that the limb sub should really be bounded away from 1. And we also need some control over the minorization volume. So indeed, the small set should not be too large. Otherwise, you might have that the minorization volume goes to 0 exponentially fast, and that will give you some trouble. So yeah, that is just one thing which was required for our results. And also, in the multidimensional case, these approximation rates could be obtained for any initial distribution. However, the argument used to show that it holds for any initial distribution does not hold in the high-dimensional setting. And here we actually do have that initialization is important. So, of course, if you start in stationarity, it holds. And if we have something like a warm start condition, then our results hold under something that can be compared to warm start condition. And in high dimensions, this is absolutely necessary because there have been some results. Is if you choose an adversarial initialization, you can get exponential in dimension scaling to reach even the bulk of the mass. And another nice finding we have is that in general, our dimension dependence can be improved. So in our general theorem, I have linear in D, but actually the bound is square root of D times the LP pi norm of F. And in general, this LP norm of F will also be of order square root of D. However, in many examples, it might be smaller. So consider the case where F is like the posterior mean, and you, by model assumption, you have that they're sparsely in the coordinates, or you have a Gaussian prior which induces some regularization which shrinks many components to 0. Then you will have that this second term is smaller, so that gives you, in those cases, an improved dimension dependence. Also, for log concave targets, we are able to give, in principle, a slightly better dimension-dependent result holds. So, yeah, to get back at the question, okay, in what settings does this one-step minorization and family of drift functions that behave well as the dimension of the state space grows holds? There have been some recent research on hierarchical models where they consider like the mixed effects model by Jun Yang and Jeffrey Rosenthal, and also recently the paper on Bayesian probit regression by Quinn and Hobart, where they show that the conditions of our theorems are satisfied in these settings. Also, we can formulate the approximation result for continuous time processes. Then we don't get the optimal rate, but we get the same rate as the M-step minorization case, but perhaps that would be better left to next talk. Okay, so now we want to go back to the question we want to answer. So given that we are running our MCMC chain and we already passed the mixing time bound, the burn-in is done, how long should we run our simulation? So how should the simulation time grow with the dimension? So what you usually have in statistic is that the dimension of your statistical model in high dimensional statistic is allowed to grow with the sample size. However, now we're a bit in the opposite scenario, where a target distribution with a certain dimension is given to us, and we need to decide how long will we run our chain. So I will ignore the dimension dependence on the state space, and you can just say, okay, if it's a posterior mean, D is equal to N, and we're interested in D components. So if I just assume this growth condition, then I get for the geometric case that we need to run at least linear in D amount of time, and so if you assume that the growth condition holds, so there's some shrinking, then I need to run at least linear in D. If I don't assume any regularization or any growth condition on this posterior mean or target mean, then I have to run my chain for at least time D squared in the high dimensional setting. And this is just the requirement such that the Markov central limit theorem holds, because that's the first thing we need in order to do uncertainty quantification and analyze these termination criteria. So in high dimensional settings, it does sound reasonable that for 1 million dimensional chain, you need at least 1 million samples. Okay. Now, estimation of the asymptotic variance. So as you remember, this thing is given by the posterior variance plus all the autocorrelation terms from the chain. And the most widely used estimator for this is the batch means method. So in equation 1, all we're doing is we are dividing the simulation output in KT batches of length LT. And for every batch, we're computing the mean. And then the batch means estimator is just a blown up version of the sample covariance matrix of these batch means. And then of course the crucial question is, how do we choose LT? There has been lots of interesting research on this, especially the paper by Dutica, Fatz, Flegel, and Jones, who's also here in the audience. And what we do, they basically show that given this Gaussian approximation result, you have desirable consistency, strong consistency even, of estimators of the asymptotic variance. And we can, by immediately plugging in our results into their theorems, we can adapt the tuning parameters, like the length of the batch size, such that also in high dimensional settings we can consistently estimate this variance matrix. Perhaps I should have written here its convergence in Frobenius norm. Okay. So indeed, by adapting this framework, we see that also in our setting, high dimensional setting, we can estimate the asymptotic variance. So what we see is that if there's a larger approximation error in your Gaussian approximation rate, you have larger batch sizes, which makes sense because the fact that you have a larger approximation error means that the process is in a sense converging more slowly to a Brownian motion, so it probably has a more complicated dependent structure, and every batch in batch means of your simulation output needs to be some representation of the process. So you do need longer batches in that sense, and as it turns out, you need to blow up the length of the batches also by the dimension, because the dimension influences your Gaussian approximation rate. And again, we adapt the results of Dutica, Fatz, and co-authors. So what we do is by our Gaussian approximation results, we see that we have to blow up the batch size by an order of psi d, which in case of some regularization is an extra square root of d. Of course, this will be on the conservative side, but at least it gives you the guarantee that you have a consistent estimation of your standard errors. Okay. Then let's look again at the termination time. So what we do, we terminate the simulation, and the volume of our confidence ellipsoid is sufficiently small. However, important thing, we have some minimum simulation threshold T star. And that is because we don't want to terminate early because of a bad estimate of our asymptotic variance. So how we choose this, we will say later. So as I mentioned before, this was first analyzed in Peter Glynn and with their paper. However, they assumed that you have a Gaussian approximation with an implicit rate. They did not have an explicit rate, so they did not. So how we extend their work by considering an explicit convergence analysis and have explicit bounds for the termination criteria, which also gives us guide how to choose this minimum simulation threshold. So the main message is, if you want, say, your posterior mean up to some precision level epsilon, you first need to make sure that you have your asymptotic covariance matrix up to a certain position. Because if you don't have your asymptotic covariance matrix, and by extension of that, your confidence ellipsoid up to a certain position, then you can say nothing about how sure you are about the posterior mean. So before you even can use this termination rule, you need to make sure that you have proper idea of the standard errors and of your confidence ellipsoids. Otherwise, this rule will not be reliable. So what we did in our explicit analysis of this termination rule, we just looked at, okay, for the entire trajectory, you need to follow when the empirical confidence ellipsoid is sufficiently close to the true confidence ellipsoid you want to measure, or its volume then is close to the volume of the true confidence ellipse with the known asymptotic variance you want to measure. And in order to be epsilon precise in those volumes, you need to at least weight 1 over epsilon to the power 4. Otherwise, you cannot know it up to precision level epsilon. So that means this minimum simulation threshold, that tells you from when can we trust our termination rule, needs to be in the geometric drift one-step minorization case 1 divided by epsilon to the power 4. And in the multi-step case, we get 1 over epsilon to the power 8, which is due to the fact that here the bound is looser. So yeah, for practice, we would suggest the 1 over epsilon to the power 4. Also, an interesting fact to note is that terminating according to your termination criteria is actually equivalent to terminating according to the effective sample size. So I should have a slide on that, but the effective sample size is the simulation time times the so this lambda f is the posterior variance divided by the MCMC variance, and this is practitioners quite often also use this, and then you say, okay, I will terminate my simulation when my effective sample size is sufficiently large. And note that if you are able to sample IID from your target, then the effective sample size would just be t. So you're looking at how many samples of my chain is equivalent. My sample from the chain is equivalent to having how many samples from, okay. The sample from my chain is equivalent to how many independent samples. Okay, but it's actually shown also in the Peter Glynn paper that simulating according to the effective sample size, using that as a termination rule is essentially the same as using that. So even in that case, you can only stop when you can only trust this estimate when you can be sure that you can trust these estimates both. And that's exactly what is represented in this table here. So before you have to sample also at least time 1 over epsilon to the power 4. And there is some multiplicative dimension-dependent penalty which ensures that also in high-dimensional settings you are sufficiently close. Okay, then we have the following theorem. Because actually, stopping for the stopping rule, you're stopping at a random time, and it's actually not guaranteed that at this random time you also have a confidence set. Actually, there in the paper by Peter Glynn, there is given a counterexample which states that if you only have a weakly consistent estimator of your variance, and you don't have, say, that the variance is consistent over the entire trajectory, that your confidence set you have doesn't have the correct coverage. So we now looked at this theorem in the high-dimensional case, and indeed we see that because also we have this Gaussian approximation result for the entire trajectory, that as epsilon tends to 0, we also in this setting have asymptotic validity of the resulting confidence set. So also in that case, the confidence set you have at a random time has the correct coverage. Okay, that was my talk. These are some of the citations, and if there are any questions, I will hear it. Yes.
Thank you very much. That's a very much talk to practitioners, so we have to talk later. But I want to ask a question. I mean, I'm a practitioner, but I'm interested in things. So what is wrong with my approach? I try to get, first of all, I realize that there's something called a mixing time.
Yeah.
Which is extremely difficult to get right.
Yes.
But if I have passed this hurdle, I go to 16 times the mixing time, then I'm sure I have at least 16 samples. And with 16 samples, independent samples, I do either Gaussian or non-Gaussian or parameterized or non-parameter-based statistics, and I can write my paper, and I'm sure that my result is correct. Why should what I'm saying is the key of the battle is to get beyond the mixing time. Why are you, I understand, then you do the boxing algorithm, and you try to get the boxing algorithm into Gaussian behavior. So why do we need, in 2024, why do we need to have Gaussian statistics? I can do lots of statistics, which is non-parametric, and get good estimates of what I obtain, if I know that the sample I obtain are the samples from pi and not from my starting distribution.
Okay, so in the following sense, I agree with you. The Gaussian statistics are just one way of ensuring that you're correct. But how do you know that 60 times your mixing time, how do you know that your posterior mean is sufficiently close?
No, I'm just saying that it's, excuse me. Yes.
But, so yeah, do you have a theoretical guarantee that for the amount of samples, let's say you start your chain in stationarity.
No, yes, but then, then I go home.
Okay,
no,
but then,
come on, then if
okay.
starting my chain, one starting from stationarity, that's not for me.
Okay.
No.
But you still need to decide, how long you run your chain, and when you have your let's say your posterior mean, you only have an estimate.
Of course.
Right? So, and every estimate needs to be accompanied with a standard error. Otherwise, how sure are we of that estimate?
Well, then there's statistics that goes beyond Gaussian.
But what do you use then? I'm just curious.
I don't know, Bootstrap, whatever. I try to. Of course, let's say, we are working in situation where the mixing time is half a year.
Yeah.
Right? That's what I'm
yeah.
or it's 5 years.
Yeah.
So on my clusters, I can of course run 100 clusters and so on.
Yeah.
But then after 5 years, I have to stop, because then funding runs out. I get old and so on. So, but then I make a prediction.
Yeah.
And what I'm just saying is that I think we are able to get reliable estimates even if you're not in the Gaussian limit.
It could be the case, but then we also need some theoretical guarantees for that, right? Because even if that's something I forgot to mention, but if you can, let's say, if you sample IID from pi, then even then in the high dimensional case, the Wasserstein distance between your sum and the Gaussian limit is lower bounded by square root of d in the case of bounded f by this. And this will roughly be, we guess in the non-bounded case, it will just be the LP norm. So even in that case, for IID factors, your distance in the CLT is lower bounded by square root of d in a result by Rio. So even then, if you have an empirical average, you need to have some type of result, how it concentrates around the thing you are just trying to estimate. And if we're being really scientific, then we have, okay, this is this estimate for the posterior mean, but yeah, an estimate without the standard error is susceptible to interpretation, right? Then it's a bit like, okay, how confident are you in this? And there could be multiple ways to do that. You could do bootstrap standard errors and show that that also works in high dimensions. But this is one approach to obtain valid standard errors in high dimensional settings.
But what I'm just saying is that, I heard this sentence, I need to run a million times beyond my, that's an ideal world.
I don't know if I said a million times beyond.
You said a million, so I said,
I thought 1 over epsilon over the power 4.
In my world, that's a million years.
No, it's 1 divided by your precision to the power 4. That I think is sufficient. Yes.
I have a naive question which is kind of related to that, which is, okay, let's say I want to do a least diffusive possible Markov chain to sample what I want, and so if I'm really good at that, I should get something where the law of large number converges very fast.
Yes.
But the diffusive behavior, so typically the fluctuations could be for a very long time scale anomalous, and so if I wait to see a Brownian motion, so the best I am at being non-diffusing and having a super fast convergence of the law of large number,
yeah,
possibly I see the CLT slower and slower, and so could this kind of situation appear, and is it an issue for this kind of criterion?
So what, if I'm understanding correctly, you have a sampler that's very non-diffusive, so it will have less, more momentum, you mean, basically?
Yes, a stupid situation would be I'm in dimension 1 and I just do a deterministic sum.
Yeah.
Okay, so it converges faster than CLT.
Yeah, then the convergence is faster because you have a smaller asymptotic variance, right? And that will have a positive influence. So I think in that case, you would even converge faster in a central limit theorem sense, right?
Yeah, so with this criterion, you wouldn't have a problem where you check whether your fluctuations are close to Gaussian and you never see that because you are too good to have fluctuations somehow. No, it's not going to happen.
Well, I would guess that the fluctuations would just be really small then, right? If you're having like deterministically running around the circles, then your convergence in the CLT will be faster, I think even. And the fluctuations will be small. And you will have a high effective sample size quite quickly, right?
Okay.
So that would also be reflected in this. That's fine.
So I can ask something. So when you were looking at you mentioned the sort of consistency of the asymptotic variance estimator in Frobenius norm.
1 second, the screen is not it's off again, but okay. Yeah, it's on again. Can you repeat your question?
Yes, yeah. So it was to do with so it's sort of two questions. So one is that when you were mentioning the consistency of the asymptotic variance estimator under batch means, let's say.
Yeah.
So the result is in
Frobenius norm.
Is that's just conventional?
It was just conventional for us to do. I think maybe a looser norm would have given maybe a better rate, but this was the one that was the most naturally to consider.
Yeah, it makes sense. I think I'm used to using operator norms because for some applications it makes a lot of sense.
I agree. Yeah.
But so a sort of related question to that is, you're doing output analysis in a way for vector outputs.
Yes.
If you're doing adaptive MCMC or something like this, you're also interested in matrix outputs and stuff like this.
Yeah.
And probably if you're measuring the convergence of the covariance matrix estimate in Frobenius norm, it probably follows from what you have. But if you wanted an operator norm or something like this, it might be a bit of extra work. Does that sort of match your intuition? Or?
I mean, if you want convergence in operator norm?
Yeah. Because for matrices, that's often the one you want.
Yeah. We also have a result regarding, I think they are, I forgot the exact relationship between them. One is perhaps square root d smaller than the other.
Yeah, there'll be some.
And then if you then have because the convergence rate is explicit and you assume that it's small o of square root of d, then you can also get convergence in the other norm, but it would give you perhaps, if it's bigger, then it would give you more requirements on your simulation time.
Yeah,
even.
Yeah, this makes sense.
But I don't know by heart now.
No, that's fine.
But indeed, you could, I think, translate it.
Okay.
Yes, but for our case, the Frobenius norm was the most natural to consider.
Yeah, that makes sense. Thank you. Do we have any more questions from the audience? Terrific. Okay, well, we can probably break from the session a little bit early.
Thank you.